All right. Well, hey, welcome to the end of week 6. After today, we are halfway done with this class, believe it or not. This quarter is just flying by. Um, well, maybe not for you guys after having had to take a quiz and gone through all that. But anyway, so today's plan, I'm going to introduce you to the last sets of identities that we're going to add to our list. And then once we're done with that, we're done with identities. We're not done using them, but we're done developing them. Okay, so I'm going to show you two sets, the product to sum and sum to product identities. And then after that, seeing how much time we have, we'll probably start talking about solving equations, which is kind of the whole point of this part of trigonometry, is getting to the point to where we can solve equations that involve the trig function. So we'll see how time goes, but maybe we'll get into that. However, before I do that, I do want to turn it over to you guys. Are there any questions you guys have regarding any of the homework or other things that we've talked about so far?
Yeah, I had a couple questions on the homework.
Sure, Jack, which ones?
Number 1 and number 6.
Can you tell me which sections, please?
Yeah, the 9.3 practice.
Okay, so 9.3, numbers 1 and 6.
Yeah, that'd be perfect.
Okay, I'll put those on the list. Any others that people would like to see? All right, well, we'll go ahead and start with those. And then if anything else comes up, just let me know. So let me go ahead and share my screen. We'll go take a look at those. So 9.3 practice, numbers 1 and 6. Okay, so let's just dive in here with number 1. So number 1 says we've got sine of x is equal to 1/7. And we know that x is in quadrant 1. So then we want to find sine of 2x, cosine of 2x, and tangent of 2x. And it said, find all this without actually finding x. All right, so we're not going to find out what the angle is. I don't care what the angle is. In fact, I don't need to know what the angle is. I can get the answers to these things just by using the identities. All right, so let me go ahead and share my whiteboard, and let's see what we can do with this guy. All right, so again, here's what we know about this angle. We know the sine of x is equal to 1/7, and they tell us that x is in quadrant 1. And this is actually really, really important, this x is in quadrant 1, because there are lots of places where sine is 1/7. There's more than one place, but we're specifically looking at the one that's in quadrant 1. All right, so here's what we want. Let's just start with sine of 2x. So what we're going to do is we're going to use the identity for sine of 2x. So we developed this a while ago, a couple days ago. And this identity is that the sine of 2x is equal to 2 sine x times cosine of x. So already we actually know what's going to go in for sine of x. I've been told the sine of x is 1/7. So if I can figure out the cosine of x, I can put that into here and actually get my value. So how are we going to get cosine knowing that sine is 1/7? What do you guys think? What can we do?
Pythagorean theorem.
All right, I love the Pythagorean. Right, so let's go to the good old sine squared plus cosine squared is equal to 1. So sine is 1/7. Squared that, so I'm going to add that to cosine squared equals 1. And I'm not sure if this is what you meant by the Pythagorean theorem. You may have meant a right triangle. I'll show you how we can do that as well. But this gives me cosine squared is 48/49. So the cosine of x is going to be the square root of that. It's going to actually be plus or minus the square root of This is 4 root 3 over 7 if you reduce it. All right, but now this is why being told it's in quadrant 1 is important, because then we can determine which of these we use, the plus or the minus. All right, so which one is it? If we're in quadrant 1, is cosine
The
positive or
plus.
negative? Yeah, thank you. So it's the positive. All right, cool. So we're going to take the positive 4 root 3 over 7, and we're going to put it in there. All right, so the sine of 2x then is going to equal 2 times 1/7 times 4 root 3 over 7, or 8 root 3 over 49. So that's the sine of that angle. Right? 2x is an angle. It's double the angle x, whatever it happens to be. But I don't actually need to know what that angle is to know its sine. I was just able to find that using the double angle identity for sine. All right, so we're going to do the same thing to get the cosine and the tangent. So now with cosine of 2x, there are actually 3 forms. We can use the one that kind of the automatic one that gets built is cosine squared minus sine squared. But we also saw that there were a couple of other forms. So we can actually use any of those that we want. We've got both sine and cosine, so we could use this one. But since we have only sine, we're given the sine, I'm going to use this last guy just so you can see how fast it is. So this is going to be 1 minus 2 times 1/7 squared. So that's 1 minus 2/49, or 47/49. And that's the same thing you would have gotten if you'd used the first form or the second form. Either way, you're good to go. All right, so there's sine and then there's cosine. So now for tangent, we need to get the tangent of 2x. Oops. Let me write all the tangent out there, Bruce. Okay, so tangent of 2x. Now, we do have a double angle identity for tangent, which is 2 tangent of x over 1 minus tangent squared x. And that would require me to find the tangent of x. But I'm not going to do that. That's too much work. What do you think I'm going to do here? What does this lazy mathematician see that's going to be faster than trying to develop tangent of x?
Sine over cosine?
Yeah. I know that this is also the same as sine of 2x over cosine of 2x. Right? That's from the quotient identity. And I already have these two numbers. Sine of 2x is right here, 8 root 3 over 49. The cosine of 2x, I already have that. It's right here, 47 over 49. So we have lots of tools, right? These identities, they're all different tools to get where we're trying to go. And, you know, pick the one that's easiest, that's most convenient, that's going to do the job the best, right? Like, you don't always grab a hammer. Sometimes you grab the screwdriver, right? Same thing here. All right, well, this is just a matter of flipping it over and multiplying. And in this case, we're going to get 8 root 3 over 47. So I check out the power of this identity, or these sets of identities, is that I still have no idea what my angle is. No clue. Right? What is x? I don't know. What is 2x? I don't know. But it doesn't really matter. I now actually know the sine, cosine, and tangent of that double angle. Okay, but I'm curious. I'm just curious. I'm going to ask you guys a question. And this isn't anything to do with the actual question on the homework. But here's my question. what quadrant is 2x in? We already know that x is in the first quadrant. And which quadrant is 2x? Come on, you got a 1 out of 4 chance. Just that's not terrible odds.
Is it quadrant 4?
I'll say quadrant 2. Why not?
All right, so I heard a quadrant 4 vote. I heard a quadrant 2 vote. Someone's got to give me a quadrant 3 and then a quadrant 1. That way we got all our bases covered, right? All right, turns out that we can answer this. Like there is a way of telling. And I'm going to give you a hint. Go back and look at what we found. Here was the sine of 2x. That was the sine value. Here's the cosine value. And here's the tangent value. And I'm going to give you another little nudge. Think about plus or minuses. So for those of you that jumped in, I think Jack, I think you said quadrant 2, and Joe, you said quadrant 4. Might have been the other way around. What do you guys think? Are you still good with your guesses?
I'm still good with my guess, yes.
Okay.
Which is quadrant 2.
Okay. Which quadrant was that again, Joe? Sorry.
Mine was 2.
2. Okay.
Yeah, I think I'm going to switch to 1 because they're all positive.
Okay. So Jack is changing his to 1. And Jack, that was a good switch. And you're exactly right. What you just said, if you look at these, sine is positive, cosine is positive, and tangent is positive. The only place where all 3 of those can be positive is in quadrant 1. So this is definitely a quadrant 1 angle. You know, quadrant 2 is not a terrible guess, actually, because if you think about angles that are in quadrant 1 between 0 and pi over 2, if you double those, that's between 0 and pi. So we're going to be somewhere in the first 2 quadrants. But it turns out this one's in quadrant number 1. So the signs, the plus or minus signs, tell you a lot, actually. That's one of the things that I definitely pay attention to. I definitely look at the plus or minus signs on my trig function because it gives me a lot in terms of where I'm located. And then I know how to, once I know what it's in, then I can find things like reference angles and all that. So knowing the quadrant is super important, which is why a lot of times, like in this case, they even told us, right, that X was in quadrant 1. All right, so is this good for question number 1 on that? Any other questions on this guy? Okay, so let's go take a look at number 6, which is the other one that was asked about in here. Okay, so this one says if tangent is equal to 11/18, and then it says in quadrant 1, then cosine of 2x equals. All right, well, this is actually really similar. This is a really similar thing to what we did last time. We're actually only finding the one of the 3. We don't have to find sine, cosine, and tangent. We're just finding cosine of 2x, and we were given different information. But let's tackle it the same way. All right, so I'm going to go ahead and switch back to the whiteboard. And I'll clear all of this. All right, so again, this is what we were told. We were told that the tangent of theta was 11/18. And theta is in quadrant 1. So we're going to try to find the cosine of 2 theta. All right, so again, cosine of 2 theta, we have 3 choices. There are 3 different options that we have for our identity. Either way, whichever one we pick, we're going to have to find something out other than tangent, right? We need to find sine and or cosine. So let's do this one with the right triangle, which is the other approach that we have for these. So if this is my theta, then my tangent is opposite over adjacent. So the opposite side is the vertical side here, and the adjacent side would be the horizontal side, which means I can find that third side by using the good old Pythagorean theorem. So c squared is going to equal 18 squared plus 11 squared, which I think is 364 plus 121. Check me on the 18 squared though, please. And then adding that together, I get 485. So that's c squared. So c is going to be the square root of 485. All right. So now we get to pick which identity we want to use. I'm going to recommend against the first one, against cosine squared minus sine squared, because that means we have to find both cosine and sine. I don't want to find both of them. So I'm going to opt for the 2 cosine squared theta minus 1. And if you ask me why, I'm going to tell you that really it's because the cosine squared bit is positive. I'd rather just subtract 1 than subtract something else. So, but it doesn't really matter. But in order to answer this, I need to know the cosine of theta. So let's think about how we get cosine. Cosine is adjacent over hypotenuse. So the adjacent side is 18. And then the hypotenuse, we just calculated that was the square root of 485. So I'm going to put that in here. And then I'm going to square it because it was cosine squared minus 1. All right, so now we do this. 18 squared, again, I think is 364. So when I double that, I get 728. 485 squared, or square root of that squared is 485. And then I'm going to subtract 1. So if I get a common denominator of 485, 728 minus 485, I believe is 243. And yeah, I'm going to leave it right there. It's 243, 485ths. I know that the homework thing, it said have it accurate to a certain number of decimal places. Well, you can punch this into your calculator and then round it. But A, I'm too lazy to do that. And B, I would rather have an exact answer than a decimal approximation, me personally. Anyway, so again, check this out. Do we know theta? Nope. Do we know 2 theta? Nope. Do we care about them? Not really. But we're able to actually determine what the cosine of that double angle is, even without knowing the angles themselves. Now, how about, I'm going to ask you the same question I asked you before. Can you tell me what quadrant 2 theta is in?
Quadrant 4.
All right, so I get a vote of quadrant 4 from Danielle. That's definitely possible. It could be in quadrant 4. What other quadrant could it be in?
1.
It could be in quadrant 1. And actually, that's the best we can say right now. Is 2 theta is either in quadrant 1 or it's in quadrant 4. But if we calculated one of the other trig functions, it doesn't matter which one, if we did sine of 2 theta or tangent of 2 theta, that would actually be enough for us to nail it down, right? Because like if we did sine of 2 theta and we got sine was positive, it's quadrant 1. If sine is negative, it's quadrant 4. Similarly, if tangent is positive, quadrant 1, tangent is negative, quadrant 4. So we don't actually have enough information at this point to say which quadrant it's in. We'd actually have to go and calculate one of the others to find out. Turns out this one's going to be quadrant 1. If you do sine of 2 theta, that's going to be a positive number. I'll let you just figure that out on your own. Well, actually, here you go. Here's how I know that. I might as well share my tricks. It's not like I did anything. I didn't actually calculate them at all. I went here. Sine of 2 theta is going to be 2 sine times cosine. Okay, so 2 is positive, obviously. Sine and cosine of theta are both going to be positive. How do I know that? What about this problem tells me both sine of theta and cosine of theta are positive? I don't know if you saw the cursor, just it was like a Ouija board. It just kind of naturally started progressing to the answer because it was quadrant 1. Theta was in quadrant 1. That tells me all of the trig functions in there are positive. So that means if I come to my double angle identity, this is going to be positive. What's its actual value? I don't know. Don't care. But I do know that it's positive. So with that, knowing that the tangent is positive and that the cosine is positive, I know that 2 theta is a quadrant 1 angle. It's the powers of the signs, man. The power of plus or minus here is incredible. And using the identities, you can actually see a lot of the time what's going to happen just by thinking about their signs. And actually, sine of 2 theta is a great one for that, because it's just a product of sine and cosine. And we know what happens if sine and cosine are the same sign or different signs, and in terms of pluses and minuses. So I actually use the double angle of sine identity to help me figure out where 2 theta is if I ever need to know. Anyway, so it wasn't magic, although maybe it was the math ghosts that led me to it. I don't know. I sometimes feel like that's the Zoom world, right? It's the math spirits. Are you there? I just asked you a question. Are you there? Anyway. All right, so is this better for number 6? Kind of see the approach. I think honestly, this is one of the reasons why I love trig, is that once you get all these tools and once you see it all, you can actually solve a lot. You can do you can figure out a lot with just a little bit of information. And I'm a puzzler. I totally am. Like, I love jigsaw puzzles. I love crossword puzzles. I'm actually not a huge fan of Sudoku. Go figure. But I'm a big puzzler, and trig is just one big puzzle. It's taking these pieces and putting them together. So anyway. All right, so hopefully that was good for those 2 questions, Jack. Were there any other homework questions we want to look at real quick before we hit those last identities?
Thank you, Bruce.
Yeah, you're welcome. Okay, well, hearing none and seeing none, then I'm going to go ahead and hop up to the whiteboard. So I'll be right back with you. All right, so we have 2 more sets of identities that we got to take care of. And you remember that big long list we have of all the identity groups? Well, we're going to add 2 more today. And the two that we're going to add to it are called the product to sum and the sum to product. And they do exactly what they sound like. Remember, the word product in math means multiply, and sum in math means add, right? And so what this is going to do is this is going to take products of sine and cosine. So sine times sine, sine times cosine, cosine times cosine. And it's going to turn them into additions. So we're going to go from multiplying to adding. The other ones, sum to product, are just going to go in reverse. There, we're going to take two signs that we're adding, and we're going to turn it into multiplication. So I will give you rationale for why we have both of these and going both directions. But we're going to start with the product of sum. Okay. Now, to derive these, we don't actually need anything new. We're actually just going to use identities we already have, and specifically, we're going to look at the sum and difference identities for sine and cosine. Okay, so let's just take a look at the two for sine real quick. Remember, we had sine of alpha plus beta. That was equal to sine of alpha cosine beta plus cosine alpha sine beta. And then the difference of angles was identical except for a minus sign there, right? So it was sine alpha cosine beta minus cosine alpha sine beta. So we developed these a while ago, but we ran into these. All right, so mathematicians being who we are, we like to fiddle with things. Like we totally are the type that need fidget spinners, and these are our fidget spinners, equations and all that. So we being who we are, mathematicians went, you know what? I'm going to actually add these guys together. I'm going to take these two equations and I'm actually just going to add them, just like it's a system of equations, just like I'm doing elimination. And really the reason to even think that, other than, well, because we're math people and we do this sort of thing, is recognize that these two pieces are identical but have opposite signs, which means if we add these together, they're going to go away. Well, that's actually kind of cool. All right, well, if you do that, check out what happens. So on the left here, we're going to have sine of alpha plus beta. And we're going to add to it sine of alpha minus beta. And on the other side, that stuff cancels. And we're left with 2 sine alpha cosine beta. Well, okay. Well, remember what we're working on? We're trying to create identities that take products to sums, or we're going to be multiplying two things together and getting instead stuff that's being added. Well, isn't that kind of what's going on here? We've got some multiplication. I mean, we got that 2. We can move that over though. But we got multiplication that's leading to addition. So if you just take that and divide by 2, you get the first of the 3 product to sum identities. We get sine of alpha times cosine of beta is equal to 1/2 sine of alpha plus beta plus sine of alpha minus beta. All right, well, there you go. That's one of them. When you have a sine times a cosine, you can actually turn it into an addition of sines. It's just those signs are going to have in them either the sum or the difference in those two angles. And this is always true. no matter what your angles happen to be. All right, so this is the one that gives us sine times cosine. Now, there are also two more identities here, and they involve sine times sine and cosine times cosine. All right, so I'm going to go ahead and just put these up here. So you have sine of alpha, sine of beta, and then cosine of alpha, cosine of beta. Because those are the three different forms you can get if you're just multiplying sines and cosines. Right? They can both be sines, they can both be cosines, or they can be one of each. Now, to get the others, you're going to do this exact same trick, but with the sum and difference of cosines. Again, recall with the sum and difference of cosines identities that they were identical with the exception of the sign in between. So you can do the same thing where you can just add them together, cancel, move stuff around. And that's what actually leads to these next two. So I'm not gonna actually derive them for you. You can just take my word for it. Or if you really want to, stop by an office hour and I'll show it to you. But it's exactly the same idea, but using the cosines. And so for the sine times sine, you get 1/2 cosine of alpha minus beta minus the cosine of alpha plus beta. And then for the cosines, you get 1/2 cosine of alpha minus beta plus the cosine of alpha plus beta. So let's go ahead and put a box around this, because those set of three, these are the product to some identities. All right, so we didn't actually do anything new. I know it felt like it, but we didn't. We just took things we already knew about and we just tweaked them a bit. Well, that's been the moral of the story actually with identities ever since the sum and difference of angles. All the rest, double angles, power reduction, half angles, now product of sum, they all come from those. All right, so let me show you where this would be useful and where this would be kind of nice to be able to do. Let's just say we had this expression that we wanted to simplify. We want to know the value of this. Let me get it up here. So for example, let's say we had the cosine of 7 pi over 12 times the sine of pi over 12. And we want to get an exact value for it. We don't want a decimal. We want an exact number. Okay, so there are actually a bunch of ways we could do this. The first is with like 7 pi over 12, we could think of that as a sum or difference of angles and go and find the cosine. We could do the same thing with sine. We could use the half angle identity for both of these, because pi over 12 is half of pi over 6, and we know everything about pi over 6. 7 pi over 12 is half of 7 pi over 6, and again, we know everything about that. It's on our chart. So we use half angle identity. So it's not like there's just one way to get there, but probably the fastest actually is going to use this product of sum. So let's look at this guy, because we've got sine and cosine being multiplied together. So we're going to use this one right here. So all we have to do is replace the alpha and beta with these two angles. But it's very important with this first one, and this is really only true for the first one, you have to be very careful about the fact that alpha is the one that's in sine and beta is the one that's in the cosine. Because multiplication is commutative. You can write it in either order. So sometimes you'll see the cosine come first. But for this one, we definitely have to put the sine's angle in for alpha and the cosine's angle in for beta. For the other two, it doesn't matter. Since it's sine times sine, calling one alpha and the other one beta, I don't care. And the same thing with cosine times cosine, calling one alpha, the other beta, it doesn't matter. This is the only one we actually have to watch out for. All right, well, if we use this identity, that's going to give us 1/2 times the sine of, so I need alpha plus beta. So alpha was my sine angle, so pi over 12, plus 7 pi over 12. And then we're going to add to that the sine of pi over 12 minus 7 pi over 12. So now let's do this, do these operations on the angles and see what we get. So this is going to give us 1/2 sine of 8 pi over 12, which is 2 pi over 3. And then pi over 12 minus 7 pi over 12 is minus 6 pi over 12, or minus pi over 2. And these are nice angles. These are angles that we can get the values for because they're on our chart. So the sine of 2 pi over 3, that's a quadrant 2 angle. So it's going to be positive, and it's going to be the same as the sine of pi over 3. And the sine of pi over 3 is √3 over 2. And then the sine of negative pi over 2, we can pull the minus sign out front because of the odd property of sine. Sine of pi over 2 is 1. So I'm going to go ahead and get a common denominator here. This is going to be √3 minus 2 all over 4. All right, there you go. There's the exact value of that product using product to sum. Now, I'm going to tell you that product to sum identity, in terms of its usefulness, where you're going to see that this is useful, again, is a calculus thing. If you're going to do the operations in calculus, derivatives and integrals, it's a lot easier when you have things being added than being multiplied. A lot. And so that's the scenario where we tend to see these anymore. So this is another one of those where I'm going to have to tell you in the future, you're going to like these. The sum to product, I'll be able to give you rationale pretty much right away. But that is one of those things that, just so you know, eventually it's going to matter. Historically, it was super big. Because think about being in the days before calculators, when you had to do everything by hand. It's a hell of a lot easier to add two numbers than to multiply them together. Right? Adding's easier than multiplying. So kind of like with logs, that was sort of a big deal. Like, oh wow, we can actually add stuff instead of multiplying. Sign me up. All right, so there you go. There are the product to sum identities and an example of union. All right, now the sum to product is just going to be going backwards. It's going to be taking two things and adding them. So sine plus sine, cosine plus cosine, right? And going in reverse. Now, how you get them, you can actually use the product to sum identities and then just do the algebra backwards. I'm not going to do that. I'm not going to torture you with that. I'm just going to give you the four of them. Okay. There are actually 4 sum to product identities. And they all have very similar form, which again probably does not surprise you. But let's just go ahead and get these up here. All right, so the first one is sine of alpha plus sine of beta. Okay, so we're going to have two signs that we're adding together. You can actually turn this into a multiplication. It's going to be 2 times the sine of alpha plus beta over 2 times the cosine of alpha minus beta over 2. If you go back and you look at the ones that I just erased, so if you had them written down, go and look at the product to sum for sine times cosine. You'll see sine times cosine was equal to 1/2. And then we had the 2 sine things that were being added. Well, that's pretty much what this is. The 1/2 comes over. We just have to change what's inside those angles because now we're just calling these things alpha and beta. All right, so there's the sine plus sine. We also have one if you have sine minus sine. So sine of alpha minus sine of beta. And this one actually also looks very, very similar, as it should. But what ends up happening here is the angles swap. So the things that are in the sine and cosine end up swapping. And really the reason for this is the oddness of sine. Because subtracting a sine is like adding the negative beta and it changes your sign. Okay, so we call them sum to product, but it also subtraction is also in there because subtraction really is adding. All right, so there are your first 2. The second 2 are the same with cosines. So we've got cosine of alpha plus cosine of beta. So this one, we get 2 cosine of alpha plus beta over 2 times the cosine of alpha minus beta over 2. That one comes from the product to sum for the cosines. If you look at cosine times cosine, that leads to this guy. And so then pretty obviously, the one that's cosine minus cosine is going to lead to sine times sine, because that was the product to sum that we saw. But this guy has one little slight variation on it. It actually has a negative out front, so it's -2 times the sine of alpha plus beta over 2 times the sine of alpha minus beta over 2. All right, so there are your 4 sum to product identities. Sine plus sine, sine minus sine, cosine plus cosine, cosine minus cosine. All right, so where they come from, the product of sum. Where the product of sum come from, the sum and difference of angles for sine and cosine. You can kind of follow the ancestry back to sum and difference of sine and cosine. So I don't know if you have kind of figured this out, but remember when we first started deriving the difference of angles for cosine, and then I drew that little picture with the circles and we did the geometry? That one geometric fact led to like half of our identities, maybe even more than half, which again, I find pretty cool. Just one little fact about the lengths of a chord on a unit circle led to all of this stuff that ends up being really useful. I know things that I find cool are definitely not cool. Just ask my kids. I have 2 adult sons. My youngest is 19, and yeah, things that dad finds cool is very subjective, right? Anyway, all right, so there you go. There are your sum to product identities. So let me show you how we can use one of these things. First, we're going to prove an identity, just to kind of keep that in our forefront of our mind. But then I'm going to give you a real reason, not just to do identities for the hell of doing identities for the practice, but a real reason why we still like sum to product. Okay, and it's a legit real thing. All right, so let's go with this identity. Let's see if we can establish this identity. Let's say we've got sine of 3x minus sine of 5x divided by cosine of 5x minus cosine of 3x, and that equals cotangent of 4x. So that probably looks suitably ugly. Not only do we have fractions, but every one of these trig functions has some sort of weird multiple angle in it. None of them are really nice, like double angles. I mean, I guess cotangent of 4, we can make that a double of 2x. But yeah, so we don't really have anything nice to do there. But check out what happens if we use sum to product. In this fraction, and I would definitely start with the fraction side, that's uglier. I've got subtraction of sines on top and subtraction of cosines on the bottom. So how about we go ahead and use these two identities? So if we use the difference of sines for the top, we're going to get 2 times the sine of 3x minus 5x over 2 times the cosine of 3x plus 5x over 2. And then on the bottom, do the same thing, but for the difference in cosines, I'm going to get a minus 2 sine of 3x plus 5x over 2 times the sine of 3x minus 5x over 2. Hold on, these are backwards. 5x minus 3x. Alpha minus beta. I'll change these two as well, even though it doesn't matter. All right, so that's where we are. Let's simplify this. Let's simplify what's in here and see what we can do about it. So first of all, 2 over minus 2, those are going to cancel and leave me a negative out front. So I'm just going to put a minus out front. 3x minus 5x is minus 2x, divided by 2 is minus x. That's the negative sine of negative x. And then I get the cosine of 8x over 2, which is 4x. So there's the top. And then the bottom, do the same thing. I'm going to get a sine of 4x. And then this is going to give me a positive 2x over 2. So just plain old sine of x. So it's starting to look good. Because think about where we're going. We want cotangent of 4x. So we'll do a couple more things. The oddness of sine means that that negative can come out front. So let's bring it out front. Negative, negative is a positive. And then I've got sine divided by sine. So sine of x over sine of x, so those things cancel. So once I do that, we're down to just cosine of 4x over sine of 4x. Which conveniently is just cotangent of 4x. So this is definitely true. we're able to establish this identity, and the sum to product identities were a great way of getting it. Again, not the only way by any stretch of the imagination, but a way. All right, so there are your sum to product. Now, I told you, I promised that I was going to show you why we want these today, other than just fiddling about with identities and stuff like that. So here's a question for you. It's a really easy question. Can you tell me all of the angles whose sine and cosine have the same value? All right, so super easy question. What angles have the same sine and cosine? Now, you can look at your chart and actually find a couple, because there are a couple on our chart. Do you see any?
Pi over 4 and 5 pi over 4.
Okay, perfect. Yeah, so pi over 4, if you go down to your chart, pi over 4, the sine and cosine are both root 2 over 2. You go a little bit further down the chart, you get to 5 pi over 4. You see the same thing. Sine and cosine are both negative root 2 over 2. So those are two places where it happens. Are there more? And I don't mean on your chart, because on your chart, yes, those are the only two places on your chart where that happens. But are there other places where sine and cosine are equal that aren't on the chart? Well, maybe not. All right, so it's a really easy question to ask, but it's not so easy of a question to answer unless we use the sum to product identity. Oh, I totally lied. This isn't where we want to use this one. This isn't going to do what I want it to do at all. It's still a good question. Still a good question. We probably need to try to answer. Scratch that. But, this will be, we'll answer this later. Oh, man, it's one of those days. I've actually, I've been in Zoom meetings since 8:30 this morning. I actually had to leave this other meeting early to get to you guys. I was glad you guys were taking a quiz because that bought me a little extra time, but yeah, I think mentally I'm done. Anyway, I apologize for that. We'll answer this question later. Well, because here's kind of where that was going. We're going to have sine of x equals cosine of x. I want to solve this equation. I can rewrite that as sine minus cosine equals 0. And that's where I wanted to go. So here's what I'm going to do instead of this. How about we answer this question? Where does cosine of x equal cosine of 3x? Yeah, this will do what I want it to do. So similar kind of question, but can you give me an angle where its cosine is the same as the cosine of the angle that's 3 times as big? It's 3 times as big. This is actually a much tougher question to answer because using the chart may or may not help, but we can't just like go across the row and all that. But so here's the question. Now, trying to answer it, like I said, would be kind of difficult, but realize that we can turn this into a different kind of equation if I just subtract. So I could make this 0 equals cosine of 3x minus cosine of x. All right, now, what I want to do is make use of the sum to product. So right now I have subtraction. Let's turn it into multiplication. All right, so that identity, that was the last one that was in our list. It's the one that starts with -2. And then we get the sine of the sum of the angles divided by 2. And we get the sine of the difference in angles divided by 2. So this was just the sum to product identity. And now, if I just simplify real quick, I get -2 times the sine of 2x times the sine of x. All right, so yay. We did some algebra and some identities, and we got here. Who cares? Well, you all should care. Because think about this. Right now, I have 3 things that are being multiplied together. We've got -2, sine of 2x, and sine of x. And those things, when multiplied together, equal 0. You remember factoring? You remember using factoring to help you solve equations? So you take your big polynomial, you factor it, and then you can take each of those factors and set them equal to 0. What you were doing there is you were making use of what's called the 0 factor property. And what that says is that if you have a bunch of numbers that are being multiplied together and the result is 0, then one of those numbers has to equal 0. And so from this, we can actually factor. And we know that this is going to be true if sine of 2x equals 0, or if sine of x equals 0. And this is a much easier question to answer. Can you tell me where an angle where sine is 0? Where does sine equal 0? Look at your chart. Which
0 and pi and 2 pi.
Okay, so 0, pi, 2 pi. We're going to see it at 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, and so on. All right, that was crazy easy to answer. As opposed to the original question, at what angles do you get the same cosine value if you triple it? Well, think about those angles, they work. 0, 0 tripled is 0, so cosine of 0 is cosine of 0. Pi, the cosine of pi was -1. 3 pi, its cosine, also -1. 2 pi, its cosine is 1, triple 6 pi, its cosine also 1. So we're starting to be able to answer that question in a much easier manner, right? So like I said, this one's going to give us 0, pi, 2 pi, 3 pi, so on down the line. Well, you can do a similar thing with this guy. And this one, we can actually do this because you may remember we had homework problems that were kind of like this, where we can do that same thing of saying, well, this is like asking where the sine of theta is equal to 0. And you go, okay, so 0, we get that when theta is 0, pi, 2 pi, 3 pi, and so on. So if we convert that back into the x's, we know 2x equals 0, or 2x equals pi, or 2x equals 2 pi, or so on down the line. Right, and so we start getting a list of possible values here. You'll notice that a lot of them are on this list, but let's take like pi over 2, for example. That's a new one. Well, the cosine of pi over 2 is 0. Tripled is 3 pi over 2, and the cosine of 3 pi over 2 is also 0. So that's another place where this is true. All right. This example is a really good example of why we still care about sum to product. When you're solving equations, especially if 0 is involved, it's way easier, like so much easier to solve those things if we have things being multiplied together instead of being added. All right. So sum to product is a lovely little identity when you're trying to actually solve equations. Okay, so just kind of keep that in mind for the future. All right. Well, looking at the clock, I see that we only have like 5 more minutes left of class. So I'm not going to go into the next topic. So let's just kind of wrap up where we are. So in terms of the class schedule, everything, we're like right on schedule, which shocks the hell out of me. I don't know that I've ever been in a trig class at the halfway point where I'm on schedule. I'm always usually behind. So hopefully that'll keep going. So we have one more section to talk about in chapter 9. We are done with identities. We've developed them all. We're still going to use them. But what we're going to do next time is we're going to start solving equations. We're going to start talking about this process and how do we go about solving equations. And you'll see that it's really systematic. There's a recipe for it once we get into the right kind of form. But we're going to make use of identity and algebra to help us get into those forms. So that's what we're going to do next time. I also want to remind you that exam number 2 is a week from today. And just so you know what's going to be on, I know I put out a message on Canvas, but not everybody looks at those. Shame on you. You should always look at them if I send them out there because they're important. But it's going to cover the last part of chapter 8. So not the section on graphing sine and cosine, but the other trig functions and the inverse trig. And then chapter 9 through this section on the sum to product and product to sum identities. Okay, so it'll be all of chapter 9 except for solving equations. But also on Tuesday, hopefully at the end of class, we'll have a little bit of time to kind of review, remind ourselves what to look at. But I want to give you ample time to start preparing for that exam. All right. So with that, I have nothing else to share. So I will just wish you guys all a very wonderful weekend. And I will see everybody on Monday.
Thanks, Bruce.
You are welcome, guys.
Thanks, Bruce.